It's PowerPoint.
Well, good afternoon, everyone. We are the FIU Terramartian Robotics team. This is Alex, Rafael, Michael, and I'm Joel. And in about a month, we'll be competing in the NASA Robotics Mining Competition. So basically, NASA's main goal is to create a presence on Mars or on the Moon. And in order to do that, they need to find a way to collect the soil from the planet's surface and refine it into usable resources such as oxygen and water. So basically, NASA, the purpose of this competition is for NASA to get some ideas from teams and how to collect, transport, and dump the soil. So these are two examples of previous year's robots. This one here has a belt system that rotates around, very similar to last year's FIU's team. And this is actually West Virginia University's robot from last year that actually won the competition. This is our proposed design. So basically, it has elements of both of the previous robots. We decided to go with the track system and then the simple scooper system. So our robot is divided into 5 different systems. We have the control systems and power, which is all the electrical and the programming. We have the scooper, the bucket, which is the big one in the back, the chassis, and the movement system. For the brain of the robot, we decided to go with an Arduino Mega 2560 with an Arduino Wi-Fi shield, which is what's going to be in contact with the laptop. To control the speed and the direction of the motors, we use a Vex Victor motor controller. And to make the actual controlling of the robot more intuitive, we decided to go with a PS3 controller. And we're going to be using a Wi-Fi camera for situational awareness. So here you can see our circuit board design. We implemented several relays and circuit breakers. The way our circuit is designed, we have it so the motors only power when we want them to power. So that saves power in the long run. Here's our actual circuit design, which is actually in this little box right here in the front. We try to make it as compact as possible because with the frame that we had to make it as compact as possible. So for the power, we decided to go with we have a 4-pack of lithium iron batteries. The 4-pack supplies a total of 13.2 volts. It supplies 9.2 amp hours. So, and then with the average power consumption of each system, the motors each draw this much. So the total power consumption, if they're all running simultaneously, was around 51.5 amps. So this makes it so the battery max runtime would be about 10.7 minutes, which is right over the length of each run of the competition.
The chassis that was given to us was actually a recycled chassis from 2 previous teams that attempted to use the chassis, and they actually failed. And that's why this chassis is called the cursed chassis, and we had all intention to break the curse. In order to break the curse, we began by modifying it. We began by cutting the forward arm and replacing it with 2 additional aluminum beams. You can see the beams here on the robot. These beams not only serve as the replacement for support for that beam, they also act as the support for the gearbox, mounting on the gearbox, and the forward arms. The next 2 beams that were added are here in the back. These 2 allow for less torque between the 2 sides of the robot from bending and aluminum, and they also help support the electronic box onto the chassis. The last modification are these 2 arms here, and these were to have the pivot point for the bucket. For the movement, we decided to use a chain tread system. The reason we decided to go with chains is that the chains grab onto sprockets much better than the previous year's belt. This would allow us to have less slippage, and our treads would not pop out. Here we have the previous designs on the suspension. One of the most difficult aspects of the robot was to try to get that nice gentle bounce on it. When we did simulations on these various designs that we did, we noticed that a lot of them were just failing completely, just off in the simulation. And this allowed us to save time and money deciding which system we can go for. You can see our first system, it looks like it was working and did everything, but the stress was extremely high here at this point, and it would cause bending. This was also verified through physical, data, because when you look at the old year's robot, the shafts that were about that size, there's 4 of them, they actually have bending. If you take the rod and you spin it, it wobbles and vibrates. So this also proved the simulation. For the construction of the chains, we bought 2 number 40 chains, and we put 4-inch bolts, connect them together. You can see here on the prototype, that's how we did it. This allowed both chains to rotate the same motion with the sprocket, and these bolts allowed us to then knit or sew plastic tiles onto the treads. What this allowed us to do is have more traction on the dirt and doesn't allow our treads to sink into the fine rigging. One of the biggest things that we had an issue with was the skateboard wheels that we initially designed the robot with, is that they kept having issues in contact with these bearings. In order to prevent that, we either add more bolts, which would add weight, or we change the system. And what we did is we decided to 3D print the sprockets, since they help save in weight and time. In order to order all these sprockets, we'd have back orders for like at least another month or 2 from all sources, eBay, Amazon, etc. So we decided to 3D print the sprockets. It took a lot of time, but it was well worth it. In the end, what happened is our entire sprocket system that we have weighs equivalent to 2 metal sprockets. So we saved about 10 to 20 pounds on sprockets, and we also saved the initial about 20 pounds modifying the suspension system as well. For the gearbox were salvaged from last year's robots. We took 4 gearboxes, dismantled them as much as we could, and we took those and we made 2 gearboxes from them. Each gearbox has 2 motor inputs and 1 output shaft. It has 2 step-ups. The first step-up is 1 to 4, and additional 1 to 4 up again. This gives us a 1 to 16 ratio for the gearbox, and then we have another 1 to 2 ratio from the gearbox sprocket to the driving sprocket of the mobile system. And here we have the 2 motor inputs and the sprocket output and the internal gearbox configuration. And here we have the overall system and how it works. We have this sprocket over here, that's our driving sprocket. What this allowed us to do is that we don't have the issue of last year's robot, that they have 2 driving sprockets with 2 individual motors. The issue that happens is that if one motor spins at an RPM that's slightly larger than the other, after a certain amount of time, it will slip, and you'll have failure in the field, which, it's not good.
Alright, so I'm going to talk to you guys about the loading scooper. So our original design for the loading scooper actually had a major flaw where the angle of release for the bucket was too small. So everything that we picked up would just get stuck in the scooper. So in order to fix that issue, we decided to go and have an obtuse angle over here. So when we brought the scooper back, everything would just slide right out and into the bucket. For the manufacturing of the scooper, we decided to go with aluminum. So we bought 2 sheets of aluminum metal, and we drew the faces of the scooper on the metals, where we gave extra fence of space of material where we could easily bend and assemble the scooper together. We bolted everything together so it would be sturdy. Another thing we did change the design is the angles of the fin and the back, where this would help guide the regolite coming out of the scooper right into the bucket and increase the structure stability of the scooper itself. So for the forearms, we decided to go with 3 actuators. 2 of them are 225-pound actuators, and those actuators are for lifting the scooper and to help dig, to bring it down to dig. And we went with 1 35-pound actuator. The sole purpose of the 35-pound actuator is to tilt the bucket. So if we have too much weight into the bucket, we can release some regolite, and as well as a secondary task of when we bring it to the hopper in the back and we need to increase the angle, we can tilt it forward to increase that angle to make it slide. So as a side view of the frame for the forward arm, we have the 2 actuators on the bottom, which take the whole weight of the bucket of the forward arm, and the one actuator just for the tilting. For our loading hopper, our unloading hopper, we had slightly unrealistic expectations where we did not realize for the volume of the bucket itself, the density of the regolite, that this frame was not going to hold it. So because of this, we're looking at about 160 pounds of BP1 for that volume. So we had to restructure, we had to fortify the structure of this bucket, which came to a secondary design for the bucket, where we have the whole structure of the bucket on all the edges and the bends to fortify it, and we added support beams on the bottom to prevent from concaving on itself. For the bucket, we had a similar manufacturing process, but the difference is we had just a single plate for the entire bottom, so it could be a single piece. And we went with the sheet metals on the side to cover it. And over here, we're showing how we're cutting the jigsaw to create the frame. And for our bucket, everything was bolted together directly to the frame. So the frame and the bucket are actually a single piece compared to the frame of the scooper, which is the actual scooper, and then a frame to hold it. This is a single piece, which helps fortify it, so it should not move independently of each other. This is the final design for our prototype. We decided to go with the color red, yellow and blue for school pride, yellow for all the acting mechanism where it goes to the dirt for picking up to releasing, and blue for all the suspension and all the brain of the robot, the entire structure in blue. And here's a short clip of our robot. Over here, we're just demonstrating the actual pickup and release. It was not to show the weight limit mechanism. So we did the tilting for the 35 actuator, the tilted forward, and the tilted back to create space for the bucket to release the slave.
Okay, I will present you all with the cost analysis of the Terramartian Prowler. First, I'm going to go over the cost that it would be to build the robot by individual sections, and then afterward, I'm going to explain our cost and the savings based on the method that we did by doing the robot as a whole. So as you can see, the total cost of the bucket and the scooper was about $200 each. The total cost of the chassis was around $200, and the forward arm was around $400. The total cost of the modifications we did to the previous design was about $150, and the total cost of the mobility system was a little over $1,300. And the total cost of the electrical components as well as the gearbox were about $600 each. So by building the system in individual sections, it would total to about $3,600, but the way we built it as a whole, leftover parts that we did from an individual section, we could carry it over to another section, and it would total to about $700. But in addition, with the parts we were able to salvage from previous designs, such as the $200 actuator, the gears for the gears for the motor, and several electrical components, we were able to save over $1,000. For global learning, there's going to be several universities around the world participating in the competition, so we would be able to analyze and study the ideas that they had. Also, the research on the Martian regolith could possibly be transferred over and used with similar minerals that are found on Earth. The standard we used were IPC and CEA for the electronics, and AMT and ASTM for most of the body. This is our updated Gantt timeline for the over 2 semesters. As you'll be able to see in the poster board slide, we had to make several modifications to our timeline because the testing and manufacturing took a little longer than expected. This is the breakdown of the work based on sections or testing and report work. And in conclusion, we found ourselves with limited time and relatively low funding, but our group was able to make the Prowler fully functional. The testing that we did on previous designs, as well as the modifications that we made to it, gave us an all-around improved design. And in the short term, we're looking to calibrate the suspension for the robot to be competition ready. And in the long term, we're looking to make the robot fully autonomous. So basically, user controls would be unnecessary. We'd also like to give special thanks to the MME lab and the robotics lab, as well as following professors, Dr. Tremonte, Dr. Tosunoglu, Dr. Redding, and Mr. Zicarelli and Mr. Pradeep for their contributions and advice with our project.
Is there any questions?
I have questions about your cost. If you could put your costing slide. Your last total cost invested, what does that mean?
That's the money the group put down.
That's what you put in. I thought someone said savings, so I'm just
The savings is the difference between these two. So we spent about $1,600 out of pocket to create it, but we've saved about $1,000 from salvaging the chassis, the gears. We salvaged the gears, we salvaged the sprockets. The actuator was one of the most expensive parts. It's about $235.
Thank you.
When is the competition?
May 18th.
May 18th?
It's a week long, May 18th to May 22nd.
And do you think that your design could come first?
Is it gonna be ready by then?
It's
Is that what
hard.
you're
No, but it's
No, you're going to be first.
But
Oh,
your
we're gonna
motivation
be
is to bring back first place.
Of course.
That's what you said.
I
So do
want
you think
to.
your design
I
could come
want to.
first?
But if you look at the videos, we're going up against teams that have been doing this for 5-10 years with, with fully working teams. We got 16 people teams, fully working labs with everything. For our lab, I have to buy half the tools to be able to operate it without having to bring the robot down every single time from the IAB lab. So there's a lot of little factors that will hinder us from actually getting first place.
But also based on their point system, like they provide field cameras, we're gonna add a camera of our own, which they give points based off that, which I think most other teams aren't using their own cameras.
Another big thing for the point system is the way they do the pointing, that you lose points for the weight, is every kilogram that your robot weighs is 8 points lost to your score. And we're looking about 7, 8. We're not really at 80 kilograms yet, but most robots are usually
We're not
above that.
100
So
pounds.
we're looking at lightweight. We kind of went for lightweight and simplicity to gain
And
points.
very compact.
Are you allowed to put any design on it? Or
Yeah.
not? So you could put the
We-
golden panther on it or
We
something?
do get points for school pride.
So you're gonna put the
That's
golden
why-
panther or
Yes.
something?
Yeah.
You gotta learn how, you gotta know how to play the game. You gotta look at all the
Yeah.
points
You gotta
maximum.
try to get the L
You gotta go
points. Yeah.
everywhere. The outreach programs, the essays, the presentations, a little bit everywhere.
Now, you said that that chassis failed. How did it fail before? It broke actually?
They tried to build something from it, and they couldn't get it. They couldn't get the components onto it, and they ended up building a completely different chassis. So this chassis has a hose.
It's a reject, not a fail.
Yeah.
So this chassis has holes everywhere, so
Yeah.
it makes it harder for me to place a beam in certain places there might be a hole for everything. However, everything fit perfectly, and anything, the holes helped me reduce more weight.
When we were designing, we used the design, we kept the chassis in mind, and we kind of worked around the chassis. We used some of the holes already there for our own system to try to incorporate it as well.
What's your takeaway from your experience doing some of your work and taking the work of others as it relates to lifelong learning experience? What's your takeaway?
I learned so much from the manufacturing. Like, I thought it was going to take me 1 month to manufacture, and it ended up taking an entire semester. I had the hardest time with the stainless steel. I burnt out so many tools, just learning to properly manufacture it. So that's one of the most valuable lessons I've learned.
And also just working as a team, because there's so many little components. Like, let's say Ralph was working on the bucket, he was working on the scooper, I was working on the electrical, Michael was working on something else. There's so many little parts that you have to be in constant communication, or else it won't fit basically. All things will fit
Yeah, so
together.
you guys cutting it with a hand
With a
saw.
jigsaw.
If you had like a bandsaw, it would have been so much better, you know, you just drop it in.
A jigsaw.
When we
also
did
have
that,
a
we
multi
did-
tool. It's a vibrating tool.
Yeah, that thing's awesome, but
We
you're
did it
crazy
from our
trying to
garage
cut that stuff with that.
originally. We did it, when we tried to start it, because we tried to have it done for you guys by January, like we promised. So we went ahead and took it upon ourselves to do it at home. So we did have a lot of tools lacking, so it was kind of a give and take.
Yeah.
What's your experience?
Basically, how they were saying with how we were using the previous chassis, you just gotta learn to work with what you got, improvise sometimes, work around certain things.
Sure, thanks. Can you talk about the volume of the two containing devices? So what are the volume of the two?
The volume of this one is tricky because it's not going to be filled up all the way. This is basically going to be about 1 inch of the ground parallel to it, and it's slowly just grazing, kind of like manufacturing. You're cutting something. It's a nice slow cut. Fill it up, maybe that small layer, and then dump it up to here. For this one, if this one gets filled halfway, it's about 50 pounds. And you don't want to push it more than 50 pounds.
When we designed it with our expectations of holding 50 pounds. We tested it to about 55 pounds, it held. So we can go over 50 pounds, but we're not trying to go over that limit, because that was kind of the expectation.
You only
to
need
keep it
20,
lightweight and sturdy.
20 kilos?
You only need
It's
10 kilograms in order to qualify for the competition. So then once you actually pass that, it's just extra points every other kilogram that you get.
So you can probably see where I'm coming from though, right?
Yes.
They look essentially the same size, right?
Yes.
So why add all of this other stuff to move material from the middle another foot to the back?
Yeah, you could
Yeah,
have put a tray only.
The thing about this is
At
that
the same
we're trying to save time by being able to load a lot without having to scoop, return.